Okay, we're going to start the unit on electrochemistry now. And we do that by looking at equations that involve oxidation and reduction. Oxidation is defined as the loss of electrons causing an increase in the oxidation number. Now, if someone were to ask me, define oxidation, Dr. Pearson, I would say oxidation is the loss of electrons. But I would be thinking it's an increase in the oxidation number. That makes more sense. So if you look at oxidation number of an element, that's 0. And if it's charged, the oxidation number is the charge. So in this particular reaction, the metal starts out at oxidation number 0 and goes to plus N. So that's the oxidation numbers. And we can see that you did increase the oxidation number. You also lost electrons. So be sure if someone asks you to define oxidation, you talk about loss of electrons, because that's what it is. But it's easier to follow in an equation if you just look at the changes in the charge number that takes place. So if you have a reduction, it's going to be just the opposite. So I wouldn't bother trying to memorize both of two alternatives. I've warned you about that before. It's too easy under pressure of an exam or the moment to forget which way it is. So if you think that oxidation is an increase in the oxidation number, a reduction is a decrease in the oxidation number. So if I had some anion, typically they would pick up electrons during reaction, nonmetals, and they would become negatively charged. So you do have a decrease from 0 to a negative number. So that is a decrease in the oxidation number. Now, we also need to talk about oxidizing agents and reducing agents. Just like an insurance agent sells you insurance, an oxidizing agent sells you oxidation. It causes oxidation to take place. And of course, a reducing agent does the opposite, okay? Causes reduction to take place, or the opposite of oxidation to take place. In any given reaction, you're going to have both. So if one element's oxidation number increases, some other element oxidation number has to decrease. And we call those types of reactions redox reactions, fusing together reduction and oxidation. They're redox reactions. And you have to have exactly the same number of electrons lost in the oxidation that you have gained in the reduction. Now, let's look at balancing redox equations. Now, those of you that had me in Gen Chem 1, I showed you a method there that I think is much, much better for balancing equations. That method will work here, but all you have to do is just pretend charge is like another element, and you balance the charge. And you can do that by doing things like adding hydrogen ions if you need more positive charge somewhere, or adding hydroxide ions if you need more negative charge somewhere, or adding electrons if you're looking at just the oxidation or reduction. So the method I showed in Gen Chem 1 works here, and it works very, very well. Often we have to put water and hydrogen ion maybe in the equation when we're balancing it. In my method, you can put the water on one side and the hydrogen ion on the other side. Doesn't matter which way you put it. When you get done, if you guessed wrong, those coefficients will come out negative, and you just flip them, put them on the other side of the arrow if the coefficient comes out negative. But since the majority of my students in Gen Chem 2 didn't have me in Gen Chem 1, I need to show you another method here. So in balancing redox reactions, you need to identify the species that is oxidized and the one that is reduced. So all you need to do is go throughout the formulas of all the elements that's present and see what their charge numbers are in the reactants. And then you go to the products and see what their charge numbers are. And then you can see uh, which element increased in an oxidation number, was oxidized, and which one decreased. And we want to pick out the formula of the ion or molecule that has that species in it. And so that's what we're going to do to separate the reaction into two half reactions. So we're going to take the species that's oxidized, we're going to go from the reactant to the product. We're going to put those two in on the different sides of the arrow. That'll be one of our half reactions. And then we will find the species that were reduced and do the same thing for it. So we'll have two half reactions. They may not total the whole reaction. They are just the ones that are involved in the oxidation and reduction. By separating it into two smaller pieces like that and balancing each one of them separately, it's much, much easier than trying to do the whole thing at once. So we're going to do an oxidation and a reduction half reaction by looking at the charges. We want to balance all of the atoms except oxygen and hydrogen in each half reaction. So if you've got chlorine or manganese or potassium, it doesn't matter, balance all of those atoms first before you balance oxygen or hydrogen. You balance oxygen by adding water to the side that needs oxygen. So if you've got 6 oxygens on the left and 8 on the right, you need 2 waters on the left. You're going to add water to the side that needs oxygen. And then you're going to balance hydrogen next. Now, I'm giving this to you in stepwise procedure because that's exactly how you have to do it. You have to do it in that order. So then we're going to balance the hydrogen atoms, and we do that by adding hydrogen ions to the side that needs hydrogen. So again, you just look at the two sides and count up the hydrogens on each side. And if one side, if the left has 6 and the right has 8, you're going to add 2 hydrogen ions to the left. You're going to balance the hydrogen by adding hydrogen ions. Don't worry about the charges yet. Now we balance charge, and we do it for each half reaction. You add electrons to the side that needs negative charge. So if your net charge during the reaction is -2 on the right, then you need 2 electrons on the left. If it's -4 on the right, you need 4 electrons on the left. So you just balance charge by adding electrons to the side that needs the negative charge. Now, by the way, if you have your net charge is positive, 3, you're going to add 3 hydrogen ions to that side, 3 electrons to that side. So you would, if your net charge is positive, then you want to subtract off the charge from the positive charge, and you make it neutral by adding enough electrons to do that. Now, when you get to this stage, now you've got 2 half reactions. Each one of them is balanced according to atoms and balanced according to charge. But one of them shows electrons as a product. The other one must show electrons as a reactant. And the total amount of electrons moved in the reaction has to be the same. So if you have to multiply each half reaction by some number so that the number of electrons gained equals to the number of electrons lost. And if the reaction is in basic solution, we're still going to use the same procedure. Now, the textbook and most of my colleagues tell you a different way to do it if you've got a basic solution. Now, I don't do that. I go on and balance just by one method. And once I've got the equation balanced the way I've done through steps 1 through 7, I've balanced it as if it was in neutral or acid solution. If they tell you the reaction is in basic solution, you remember you can't have hydrogen ions in a solution that is basic. They're going to react with the hydrogen ions. So if the reaction is in basic solution, the hydrogen, and there's hydrogen ions showing in the equation, you add an equal number of hydroxide ions to both sides, and then the hydrogen and the hydroxide will form water on the one side, and you will show OH is probably on the other side. And that is okay in basic solution to show hydroxide ions. If it's in acid solution, either as a reactant or a product, you can show hydrogen ions. Okay. Now, we're most interested in those reactions that are spontaneous. And remember, we've already addressed that issue talking about the Gibbs free energy. If the Gibbs free energy for a process is negative, that process is spontaneous. Well, electrochemical reactions can be spontaneous as well. A spontaneous electrochemical reaction is called a voltaic or galvanic cell. Voltaic comes from like voltage. So if you think about a battery has a voltage, a little flashlight battery is 1.5 volts. And so the reaction that's taking place inside that battery is a spontaneous reaction. So you wind up generating a voltage. And spontaneous reactions are called voltaic cells or galvanic cells. Again, you've got two half reactions for a voltaic cell, and they have to be separated from each other. Because if you just put them together in the same solution, they'll react all by themselves. You won't generate an external voltage in that case. So inside your battery, the two half reactions are separated. They're often separated by some kind of a membrane or maybe a piece of filter paper soaked in salt water. Something to keep the ions apart, but does let charge ions cross it. So the two half reactions are separated from each other. We separate them with what's called a salt bridge. And if you had one of the reactions in one beaker and the other reaction in the other beaker, and you put two electrodes in, nothing's going to happen because you don't have the circuit completed. But if you take a piece of filter paper and soak it in salt water to make it conductive, and then hang it in the solution on one beaker into this over and into the solution in the other beaker, you have a pathway for charge to go through that salt bridge. And sometimes it's something that simple. That's what we do in lab. Or you can have a little U-tube, glass tube that's filled with potassium chloride gel that you can put inside that, and then just hang that real bridge between the two beakers. Now, the energy of the cell causes an electric current, and that's a battery, and that's what we talked about a moment ago, batteries. Now, which one? We have two electrodes. One's called the cathode, and the other one is called the anode. Now, I know books, and a lot of times students are taught that the cathode is one charge or the anode is the opposite charge. Well, that is true, but you can't say the cathode's always negative or the cathode's always positive. No. The key is reduction occurs at the cathode of the cell. So in whichever one of those beakers reduction is taking place, whichever one of the half reactions reduction is taking place, that's the cathode of the cell. And the anode is the other one. Oxidation occurs at the anode. Now, the way I remembered these was reduction and cathode start with consonants. Oxidation in anode starts with vowels. Okay, if it works, fellas. All right, let's look at some problems now. We want to identify the species that is oxidized and the one that is reduced. And we're going to be coming up shortly, I guess, on the end of the class period. I will continue the recording and I will upload the rest of it if you have to leave at 1:35. Okay. All right. So we want to identify the species that is oxidized for this reaction. I'm looking at copper reacting with nitric acid. It makes copper 2 nitrate and nitric oxide. Now, if you look at this, copper goes from 0 on the left to +2 on the right. Now, how in the world do I know it's +2? Because I memorized that nitrate was NO3 - 1. And there's 2 of them in this formula. So copper has to be +2. So copper goes from 0 to 2. Hey, that's oxidation, right? Okay. Now, let's look at the other species. Which one is reduced? Well, if I'm counting up oxidation numbers, oxygen is always -2, except in peroxides, and this is definitely not a peroxide, it's a nitrate. So oxygen is -2, there's 3 of them. So that gives us a -6 total. And let's see. So I've got -6 for the oxygens, and I've got a +1 for the hydrogen. That means the nitrogen has to be +5, because +5 + 1 would be +6, and -6 would give me 0. So the nitrogen is a +5 on this side. It's going to be +5 in this nitrate as well, same kind of formula, but it's not here. It's combined with oxygen here, and oxygen is -2. Nitrogen is +2 then in this one. So nitrogen goes from +5 in the nitric acid on the left to +2 in the nitric oxide or nitrogen monoxide on the right. So nitric acid is going to be reduced. So we've done that. Which is the oxidizing agent? Well, the oxidizing agent is itself reduced because that's what we said. The species that causes something else to be oxidized then is the oxidizing agent. Since copper was oxidized, the species that caused that was nitric acid. So nitric acid is going to be reduced, and the oxidizing agent will be the nitric acid. Reducing agent would be the other one. Again, I wouldn't try to memorize both of those. Just apply the definitions each time. Okay, so now we want to separate these into their half reactions. I've got copper going to copper +2. I've got nitric acid going to NO. Remember what I said, we're going to pick out the one species on the left that's oxidized and the one species on the right, on the left that's reduced, and we're going to pair those things together. Just 2 of them if we can do that, and we can here. Okay, now the only thing I need to do to balance this equation is balance the atoms, and the atoms are already balanced. I just need to balance the charge. Charge on the left is 0, so I have to add 2 negative charges on the right, 2 electrons, in order that the charge on the right be 0 as well. Now, we do have some atoms to balance here, and we said we're going to balance oxygen first. We got 3 oxygens on the left and 1 on the right. So we have to add 2 more water molecules. Remember, to balance oxygen, we add water. So we add 2 water molecules so that I've got 3 oxygens showing on both sides. Now nitrogen and oxygen are both balanced. Now we balance hydrogen by adding hydrogen ion to the side that needs charge. So if I look here, I've got 4 hydrogens on this side, but only 1 over here. I'm going to need to add 3 more hydrogen ions. Now I've got 3 plus 1 is 4. I've got 4 hydrogen ions showing on both sides, or 4 hydrogen atoms showing on both sides. So now the only thing I have to do is balance charge, and I can balance charge by adding 3 negative charges to the left. Notice the right-hand side is all 0, 0 on the right, so I have to have 0 on the left. So 3 plus 3 minus gives me 0. So I've got 3 electrons. Now each of my half reactions are balanced completely with both atoms and charge. The next step is to make sure that we have the same number of electrons gained and lost. We can do that by multiplying each equation through by some number. I want to multiply them by a number that both 3 and 2 will divide into evenly. All right, well, that's going to be 6 is going to be the total that I want. So I need to multiply the first equation through by 3 and the second equation through by 2. So when I do that and do that, I've got the same number of electrons gained and lost. Those would cancel. My total reaction then would be like this for the net ionic equation for this reaction. So I've got copper and I've got nitric acid and 6 hydrogen ions. If we checked out, everything should balance now in this equation. All right. Now, I'll tell you, I'm going to show you a shorthand notation that describes this overall equation, and we'll have some reasons to look at that. Now, if you look at the way it's written, I've got copper and copper plus 2. Now, that was oxidized. So copper goes from copper plus 2. They're in different phases. Copper is a solid, and copper plus 2 is aqueous. We separate things in the same, in different phases with a little diagonal line in this notation. So we have the oxidation is on the left, reduction is on the right. Now, actually, that's the way I remember it. Reduction and right is easier for me to associate together than oxidation and left. So reduction occurs on the right. This little thing here in the middle is for a salt bridge. It's something separating that separates the oxidation side from the reduction side. And so this is giving me now a salt bridge is a double line. Now, if we look at what's on the right, this is reduction. I'm going to have NO3 is going from the NO3 and the nitric acid is going to NO here. So the NO3 ion goes to NO gas. Now, the NO3 is aqueous. The NO is gaseous. They have to be separated by a little line, diagonal line. Now, what's the PT over here? Well, the two outside things in this notation, this shorthand notation, is what you have to connect to the outside world, and you have to carry a current out there. We do that by using a platinum electrode. If we stick the platinum electrode into the side of that cell that's got the nitric acid in it, we can connect that cell through a wire externally to the copper, and that creates our voltaic cell. So this shorthand notation, we put reduction on the right. If none of these things are conductors, you'll need a platinum electrode. It's an inert electrode, and that's what we always use. It doesn't cause the voltage to change by using platinum. If you use another metal in there, you got another problem. So don't do that. Okay, but if you must have a conductor that you could clip a wire onto, one on the left, copper, and platinum on the right. And then the copper is going to be sticking into the solution that has the copper plus 2 ion in it. And the platinum is going to be sticking in the solution that has the nitric acid in it. and we have the outside wires can be connected to the outside world with this. Okay, we'll do some more examples as we go along, and it'll make a little bit more sense. Okay, now here is a much more difficult problem to to do, but I wanted to pick a real difficult example for me to work through, and then if you can follow this one, you can probably follow anything that I'm going to do. Let's look at chromium. Chromium in here I said is plus 3. Well, how in the world do I know? Because it's combined with iodine. Iodine's in group 7 as a nonmetal. All the group 7 ions are -1. So that makes chromium plus 3. So iodine is -1 in this one on this side, and chromium is plus 3. Chromium on this side, it's in chromate ion, and again, oxygen is -2. 4 times -2 is -8. I must have a plus 6 here. Plus 6 with -8 gives me a -2 charge that I'm required to have for chromate. So chromium is going from plus 3 to plus 6. It's going to be oxidized. Now let's look at the iodine that we looked at a while ago. Chromium, iodine is -1. And over here, iodine is not -1 here. What is it? Well, oxygen is -2. 4 of them is -8. Iodine has to be plus 7 in order for it to go to -1. Plus 7 minus 8 gives me -1 for the charge of the iodate ion. So chromium 3 iodide is a reducing agent, and now because the chromium is being oxidized. Now look at chlorine. Chlorine's going from 0 to -1/2, so we're good. Cl2 is being reduced. Its oxidation number is decreasing from 0 to -1. So chlorine is going to be the oxidizing agent. Now, we got to put our two half reactions together. And if you look at that, we got chromium 3 iodide, and we're going to iodate here. Chromium is already balanced, one on each side. We need to balance iodine next. We do that by putting a 3 in front of the iodate ion. That will balance chromium and iodine at this stage. Now the next element we have to balance is oxygen for water. So how many oxygens do we have? We have 3 times 4 is 12, plus 4 more. Okay, 16. So we need to put 16 waters on the left in order to have a total of 16 oxygens on each side. Now we've got chromium, iodine, and oxygen balanced. We've introduced hydrogen that's not balanced, so we got to balance hydrogen. We got 32 on the left, so we have to add 32 hydrogen ions on the right. Now at this stage, all of the atoms are balanced. Charge, though, is not. On the left-hand side, you can see we've got 0 charge, so we got to make this one 0 over here. So we can do that by adding 27 electrons. So 27 negative charges, and that would be 3 more. That's 30, 32. So we've got 32 negative charges on the left and 32 positive charges on the right. So we're good. Now, chlorine's a little easier to balance. That half reaction, I just need a 2 to make the chlorine balance. And then I need 2 electrons on the left to make that the same. Now, the number of electrons used up on this side is 2. The number we have over here is 27. You have to multiply the first equation through by 2 and the bottom equation through by 27 in order to make that balance. So if you do that, this is what you're going to get. We doubled everything that we had in the first reaction, and we multiplied the second by 27. Now notice we do have 54 electrons on the left and 54 on the right. So the number of electrons gained by this is equal to the number of electrons lost by this one. Now we combine the two half reactions, and we wind up with this reaction. All we've done is just canceled out the 54 electrons from both sides and then put everything together. All of the reactants on the left and all of the products on the right. And now we're balanced. Now, suppose I need to convert this to basic solution. And in fact, this does have to be in basic solution chemically. Iodate's not very stable in acid solution. And chromate, for that matter, is more stable in basic than it is in acid. So if we convert it to basic solution, all we're going to do, we're not going to go back and start all over and do it a different way. All we're going to do is just go right here, and we say we've got 64 OH ions on the right, and we've got no 64 H plus ions on the right, and no H plus on the left. So I'm going to add 64 OH ions to both sides. And when I do that, the 64 OHs and 64 H plus makes 64 waters. We add 32 over here, so we can cancel out 32 of them. And so all we've got now is this. And if you've done this correctly, it should completely balance. And if you follow through this one, this would have to be about as hard as it gets. Okay, so here's a checkpoint on this that you can do. It's a similar one, but it's a little easier, not a lot, but a little easier than the one I just did with you. And be sure you can do this. Don't just look at it and say, oh, okay, I probably do that. No, actually do it. Work it out and see if when you're done, you've got everything balanced and all the charges, all the atoms, everything balances. It is okay to still have charge in the overall balanced equation because what we're dealing with is just the net ionic equation. So please do this. I'd prefer that if you need to talk or need help, that you talk to each other on the discussion section of D2L. And then later on, if you need help with this one, I would do it for you, but it's really to your advantage to learn how to do them. I've only shown you one example and only given you one to do. You ought to go to the textbook and look for some other redox equations to balance, just to be sure that you can do it. Frankly, the ones in the book are going to be easier, I think, than anything except the first one I did in here. Okay, well, that completes the lesson for today. And I'm going to stop the recording now. And